Hi, this is my video lab report on Lab 1, which uses constant velocity motion and Newton's second law, ultimately showing an observed object nearly in constant velocity. This is the video I made in Tracker using a roll of tape as a system, meaning the object that we're observing and everything else is the surroundings. The assumption here is that the force equals out to zero, though this is not the case in reality, and this is what we use when making the model. I added a calibration stick for the diameter of the roll of tape and also put my origin at the center of the roll of tape with the positive x direction going right and positive y direction pointing up. For clarification, the constant velocity motion, which is supposedly observed here, means that the object is neither speeding up nor slowing down as seen in this video. One thing to note about the axes here is that it would change the results a little bit depending on what is chosen. For example, if my positive x direction had been instead to the left, the position would have been shown to be positive. However, the absolute value in meters would be the same, just with the graph flipped in the positive direction rather than negative. To be using GlowScript, I compared the first two data points and found the initial velocity to be used in my model. In the code, I added the initial conditions for my tracker data, including the mass and change in time over each iteration of my loop, which was chosen to be very small as we generally use Newton's second law to predict only a tiny bit into the future. In our case, the basic idea of Newton's second law, which is that the change in momentum is equal in magnitude and direction to the forces applied to an object, has been rearranged into the velocity update formula, which allows us to use an initial velocity, a force and mass, and a change in time to predict the final velocity over a small amount of time, hence why we chose 0.01 seconds earlier in the code. This while loop used a velocity update formula for every 0.01 second change in time all the way up to 1.3 seconds, which was the time of our last experimental observation. There are a couple things to note here. For one, I had to change the starter code to actually reflect both the velocity and position update formulas. Also, because our force was assumed to be zero, the mass of the object does not actually matter following the velocity update formula. Now, in order to actually assume a force of zero, we could say that the force of gravity pulling down is balanced out by the force of the table pushing up on the roll of tape. In terms of horizontal motion, I chose a segment of my video which showed the roll of tape moving at what is assumed to be constant velocity as it was after it finished speeding up from my initial push, and there was nothing acting on it from the other direction if we aren't taking friction into account. Looking at the comparison data, it is clear that there were some differences in the experiment versus the model. First, the reason they are essentially identical at the very start is because we chose the initial conditions for the model based on our experiment. Later on, the lines are not so close. One explanation for this could be that the roll of tape started drifting toward the back or the front of the table, causing the experimental position to be different. As well as this, it could have been simple human error in placing the point mass, as it could have been in a different spot than the exact center in any direction. Though I do not have a different, more precise experiment to prove this, it would seem that my object really did show near constant velocity, at least for some segment of the video. The model based off of a genuine zero force environment nearly matched the real world experiment for some amount of time, and it is likely that the major difference near the end is at least mostly due to human error.